Chapter 7. In this chapter, we will learn how to name alkenes, how to label them E and Z or cis and trans, how to figure out their stability through heat of hydrogenation, and we will also learn how to figure out IHD, index of hydrogen deficiency. In the next part, we will be learning their reactions, E1, E2, whether we're going to be making an alkene through the use of alkyl halides or making an alkene through the use of alcohols. We will see the difference in terms of reactivity and reaction type when we discuss that in the following part. In terms of alkenes, we know already it's a chemical formula of CnH2n. That means you're always going to have the less than the maximum number of hydrogens if you are going from an alkane to an alkene. So it's an unsaturated form of hydrocarbons, and the double bond is more reactive than a single bond in an alkane due to the fact that there is a pi bond. So every single double bond in an alkene, it consists of sigma bond and a pi bond. The sigma bond will be resulting from the overlap of an sp2 and an sp2 coming from the two carbons. And every single pi bond, we know already it's going to require a set of p orbitals to overlap. So for a single pi bond to be made or to be formed, you're going to require basically one p orbital from one carbon and another p orbital from the other. And the overlap will always be above and below the bond axis. Above and below the bond axis. It's different than a sigma bond. The sigma bond will allow the electron density to rotate around the bond axis. But the pi bond is going to require the overlap to be above and below. And that basically justifies how the pi bond is more reactive than a sigma bond. It's easier to break. It's going to basically have the p orbitals. Therefore, it will be easier to be consumed to form new sigma bonds. But in terms of sigma bond, requires much more energy to break due to the involvement of any s-type orbitals. S or sp2 or sp3 or sp will always make that bond a stronger bond than having bonds being formed through p orbital overlap. And of course, the bond length is also going to be impacted. The fact that you have a double bond, that means bond order of 2, single bond will be bond order of 1. The higher the bond order, the shorter the bond will be. And the shorter the bond will be, the stronger it is. So that's why in terms of comparing a double bond to a single bond, of course, double bond will require more energy to break. But when I say pi bond versus sigma bond, pi bond will be much more easier to break than a sigma bond. Keep that in mind, due to the fact that there is an overlap above and below the bond axis. There is no such thing that a cis will give me a trans. So yes, we learned in the alkane chapter that there is always a rotation of the groups that will result in conformers, going from staggered to eclipse, going back to staggered, going back to eclipse, and so forth. And we learned that the eclipse has a full eclipse or syn, and you have also the regular eclipse. And the staggered, you have the gauche, and you have the anti. But when it comes to alkenes, the fact that alkene unit is a rigid bond, it doesn't allow for rotation. Therefore, once the structure is a cis, it stays cis. Once it's a trans, it stays trans. And that's why we label them geometric isomers. The spatial arrangement, it's due to the presence of the double bond that makes the configuration of the structure. Alkene is a stereocenter, but it's not a chiral center. Alkene is a stereocenter, but it's not a chiral center. The definition of a stereocenter, when you switch two groups from either side of the alkene, will generate a stereoisomer. And that's why cis and trans are stereoisomers. And to be more correct, they are geometric isomers. In order for it to go from one to another, you're going to have to break the entire bond to basically generate the other structure, and which is not possible to do it on its own. Unsaturation. There is something called index of hydrogen deficiency, IHD. It's important to figure out how to calculate IHD. So if I'm given a chemical formula and I'm asked figure out all possible structures for this chemical formula. Then if I'm going to start randomly connect atoms, it's going to take me longer to figure out the full answer to the question. The faster way of doing this is to figure out IHD that will basically eliminate choices among the ones that I may be thinking about. IHD tells me how many hydrogens are missing from a chemical formula. And when I figure that out, it basically, it eliminates if the structure has a single bond versus double bond. The structure has a ring versus a phenyl. If the structure has carbonyl versus a C single bond O. It will always make it easier for us to figure out an answer to a question like this. So what is IHD? IHD is basically a chemical formula that you're going to need to keep in mind, which is it's 2 times number of carbons plus 2, 2 times number of carbons plus 2. That tells me how many hydrogens I will have in the compound if it would have been a saturated alkene. Next, add the number of nitrogens. So 2 times number of carbons plus 2 plus nitrogens. What if there's no nitrogens at all? Then that will be basically eliminated from the equation, or if you just plug in a 0. Next, minus number of hydrogens, halogens included. So if I have 14 hydrogens, and I will have 14 in there. If I have 12 and 2 halogens, I will have 14 in there. All right, so 2 times number of carbons plus 2 plus nitrogen minus number of hydrogens, and the entire thing will be divided by 2. The entire equation will be divided by 2. Here's an example. I have a C5H8. 2 times number of carbons plus 2. So that's 2 times 5 plus 2. So that's 12. Plus nitrogen, but there's no nitrogen. So that's 0. So 12 minus number of hydrogens, 8. So that's 4. Divided by 2, that will be 2. What does IHD of 2 means? That means I have 2 unsaturation units. These 2 unsaturation units can be 2 double bonds, a double bond and a ring, or 2 rings. So that will help me figure out what would the structure be when I'm answering a question, giving me a chemical formula, find out all possible structures, which is a very common question to ask in these chapters. Here's another example. C4H7Br. Once again, the equation is your responsibility to figure out what the equation is when it comes to a question in an exam or a quiz. It will not be given to you in an exam handout. The equation, once again, it's 2 times number of carbons plus 2 plus nitrogen minus number of hydrogens, and the entire thing is divided by 2. How many nitrogens should I add? Depends how many nitrogens in the chemical formula. If there are 3, you add 3. If there are 5, you add 5. If there is 1, you add 1. All right, C4H7Br. 2 times number of carbons plus 2. So that's 2 times 4 plus 2. So that's 10. Minus number of hydrogens, halogens included. So that's 8. So 10 minus 8 divided by 2. That will be 1. What does 1 mean? I could have a triple bond. Or sorry, I could have a double bond, or I could have a ring. That's what this IHD of 1 means. Okay. Back to that IHD of 2, I could have also a triple bond. Triple bond, it's IHD of 2. That's why basically what 2 could also mean. In addition to having 2 rings or 2 double bonds or a ring on a double bond, you could also have a triple bond. A single triple bond will equal IHD of 1. So that's how basically we find out the unsaturation. Here's an example where the nitrogen exists in a chemical formula. 2 times number of carbons plus 2, so that's 14. Plus nitrogen, that's 15. Minus number of hydrogens, that's 7. So 8 divided by 2, that will be 4. What does 4 mean? Again, there's a lot of choices here. I could have a phenyl ring. Phenyl means you have 3 double bonds and a ring, so that's 4. Or I could have other choices. 4 double bonds, 4 rings, 2 double bonds, 2 rings, 2 alkyne units. You could have several choices now. But it makes your answering the question of a chemical formula to give all the possible structures for an easier approach than knowing nothing about the unsaturation units. IUPAC. It's very important that we learn how to name alkenes. Depending on the structure of the alkene, whether it's a straight chain or a cyclic, the set of rules, they vary a little. If it's a straight chain, you're always going to find the longest chain of carbons the alkene is part of, and you always want to number the alkene, the straight chain from the side that's closest to the alkene. Keep that in mind. Alkene is a functional group, so if I have a halide or an alkyl group versus an alkene, which one would I give the priority in terms of numbering? Well, of course, the alkene. So here's a structure where I have basically a 4-carbon chain, so numbering from left to right, following the green as the most recent IUPAC set of rules. What do I have? I have a but 1-ene. The unit of the alkene where it is has to be shown actually within the parent name. So this would sound like an alkene, but I will have to indicate the position of the alkene within the parent name. And that's why the new system has but 1-ene instead of 1-butene. You still have some textbooks do use the top format, which is also okay. But in our case, in terms of a homework assignment or an exam or a quiz, you are required to know the new set of rules. Here's another one. If you have basically pent 1-ene. Here's another one where you have basically the alkene is on the carbon number 2, so that would be but 2-ene, pent 2-ene, and here's a cyclohexene. Cyclohexene. Do I need to say cyclohex 1-ene? No, you do not. When it's a cyclic alkene, we assume the alkene unit would be 1 and 2. And then every single substituent would be numbered based on the lower numbering possible. So if I have this structure right here, 1, 2, or 1 at the bottom, 2 where the methyl is. Of course, the fact that the alkene will be 1, 2 either way, then obviously the rule that overrides here is the substituent to be on number 1 rather than number 2. So what would the name be? 1-methyl cyclopentene. How about this one? Definitely 1, 2 for the 2 alkene, and 3 would be the methyl. Can somebody might say, okay, can I number the alkene from one side to give a methyl carbon number 2 numbering? No, you cannot. The alkene within the cyclic alkene has to be given number 1 and 2. So this would be named 3-methyl cyclopentene. There's no reason to say 3-methyl cyclopent 1-ene. You are being redundant in here. So again, that's different from the straight chain. Straight chain, you will have to indicate the number of the alkene, the position of the alkene unit, regardless, even if it's number 1. But in the cyclic, you do not indicate the position of it, unless there is basically a functional group that overrides the alkene, and we'll see that in a second. So here is multiple units of alkene. So how would I indicate that in the name? I would be using the Greek prefixes, which is the di, tri, tetra, and so forth. So these will be used in here. So since I have 2 alkenes, what are they? One is number 1, and one is on number 3. So this would basically 4 carbons. So you have a buta, 1,3-diene. So it's gonna sound as an alka-diene. So this new system, it pushes us basically to indicate the position within the parent name. That's why you see it written as buta 1,3-diene. Here's a 3 alkene unit, so hepta 1,3,5-triene, and here is basically a cyclic form of this 8-member ring. So you have a cycloocta 1,3,5,7 tetraene. Tetraene means you have 4 alkene units on position number 1, 2, 1, 3, 5, and 7. So what if I have an alkene unit within a substituent? Then it depends. If it's a CH2 double bond, so this is the substituent, that would be a methylene group. But if it's a CH2, this would become a vinyl group. So the difference between a vinyl group and a methylene group is an extra carbon in the vinyl group. So here's a cyclic hexene. It's a cyclohexene if there was no methylene in there. But the fact that it's a methylene, the number 1 would be this side of the alkene, then 2, then carbon number 3 would be right there. So what would the name be? 3-methylene cyclohexene. 3-methylene cyclohexene. Here's a 6-member ring. So we have 1,
2, 3. So you number from left to right rather than from right to left. Why? Because right to left would be 1, 2, 3, 4. So the substituent becomes a number 4 versus number 3 if you would be numbering from the left. So you would number the left hand side first to give the substituent a lower numbering. What would the name be? 3-vinyl hexa 1,5-diene. Cis and trans. We've seen this in chapter 1, and we've seen it also in structures that are cyclic alkanes. So cis and trans is common to be used to label alkenes and to label cyclic alkanes. Now, there is a new system we also use in naming alkenes, so more of a formal labeling of the configuration. That's E and Z. We'll come to it in a minute. But let's just remind ourselves, what would make the structure of an alkene cis? What would make a structure of an alkene trans? The two groups that are the higher in priority cross the alkene unit. If they're facing the same side, that would be cis. If they are facing the opposite side, that will be trans. So if I have this structure, the fact that this group is bigger than hydrogen and this group is bigger than hydrogen, these set of bigger groups are basically facing the same side. That's why it's a cis. So what would the name now be? The fact it's a cis or trans, I have to indicate that in the name. And cis trans act as prefixes, need to be listed in front of the name. So I would have basically cis pent 2-ene or trans pent 2-ene. So it depends. How about these two? Are they cis or trans? They are neither. Why? Because the fact that there is one side of the alkene has the same group, one side of the alkene has the same group, that automatically roll it out being a cis or trans. Because in order for it to be a cis and trans, it has to have two different groups on each side of the alkene. Each side of the alkene. Can I have the bigger groups at the end facing the same side different or the same? Yes. Either way, it's valid. And you could see this as an example right here. So you could see the two groups are being different. I could have a methyl here, though. Methyl and methyl will still give me a cis isomer. Cyclic tend to be always a cis form unless it becomes basically larger rings. So in those structures, you may end up having trans or cis. So every single thing that you see here, for example, you have a cyclohexene or cyclooctene, you could see clearly that the favored form would be the cis across that alkene unit. But when you have a 10-member ring, you could see that you could have the possibility of cis and trans. So that's important to keep in mind. So take that double bond in the cyclooctene and turn it around. You will never get a trans form. But this alkene in the 10-member ring, you could turn it around and you could see that you could have a cis or trans. Depends on where it is. EZ nomenclature. Z usually refers to the cis alkene. E refers to the trans alkene. And it's important to keep this in mind that E and Z cannot be used in the cyclic alkanes. If I have a trans alkane, I cannot say Z, or I cannot say E trans or trans cycloalkane can also be labeled as an E. No, that is invalid. E and Z are more for the alkene units only. So using a Canning-Gold-Krylov convention, you will assign priorities based on atomic number, just like how you would label the groups across a chiral center. So Z, that will be basically for a cis, and E, that will be for a trans. That's how it is. So here's an example where you could have basically the name of the compound is 1-bromo, 1-chloropropene. I could say trans, or the more formal would be labeling it E. So E is think of it as the IUPAC way of naming an alkene rather than using cis and trans. So here, as you could see, that across the alkene, carbon number 1, which is a carbonyl, you're going to get higher priority than the CH2, and the ethyl would be higher priority than the methyl. So across the alkene, they are opposite. Therefore, it's an E isomer. The Z isomer would be basically having the two bigger groups the same side. And here's another example where you could see that when there's more than one configuration of an alkene, you will have to indicate the position of that alkene.
So in previously, we could see in here there is only one configuration, therefore you've seen the E being used in front of the name. But if there is more than one, I will name the structure based on numbering the chain that has the alkene units from the side that's close up to the alkene unit. And once I'm done with that, I'm going to find that the name of the compound would be 3-bromo-octa-3,5-diene. Once I'm done with that, I need to recognize that there is an E and Z configuration here. 3, I will basically label Br bigger than ethyl, and this group will be bigger than hydrogen. So the fact that the bigger groups are Z, that means I have to say 3Z, comma, and 5, I see it's a trans, which is E when it comes to IUPAC naming. So this name now becomes 3Z, 5E, 3-bromo-octa-3,5-diene. Imagine if you would be using cis and trans. What are you going to say? 3 cis, 5 trans? That doesn't even sound right. So that's why E and Z are the formal, more acceptable way of naming alkenes that do have trans and cis configuration. And the last thing I want to talk about in this part is the heat of hydrogenation. Heat of hydrogenation, which is talking about basically a reaction of an alkene with hydrogen in presence of a catalyst. Hydrogen as gas and catalyst as being platinum, nickel, palladium. What would the outcome of a hydrogenation or alkene be? Always the corresponding alkane. And this reaction happened to be exothermic. When I say exothermic, it releases heat. How do we use the heat factor to determine the stability of alkene? What's been observed that when hydrogenation of alkenes take place, the more exothermic the reaction is, the more indicative that the alkene is unstable. So if I have alkene A versus alkene B, like this one, for example, I have but-1-ene and trans-but-2-ene. What's the difference between the two? This one is mono-substituted. So across the alkene unit, there is only one carbon attached. And here, across the alkene unit, I have 2 carbons attached. So that's a di-substituted one. What am I noticing here? The mono-substituted, it releases 125.9 kilojoule per mole. The di-substituted releases 114.6 kilojoule per mole. So what does that tell me? Again, the more substituted the alkene, the less energy it's going to release. Because the more energy the hydrogenation reaction does have, that indicates the unstable the alkene, or the less stable the alkene will be. So as an outcome, you're going to have to keep in mind that ranking alkenes will always be as the following. Tetra-substituted is when you have 4 carbons attached into the alkene unit. Those 4 carbons being there is going to make it the most stable alkene possible. What would be next? Tri-substituted, basically having 3 carbons attached. Whether it's methyl or ethyl or anything, the fact that there are 3 carbons attached, that makes it tri-substituted. It's less stable than a tetra-substituted, but it's more stable than a di-substituted. Di-substituted has 3 forms. It could be a cis, that's the least stable di-substituted form. Geminal, when you have the 2 groups in the same side of the alkene. And trans, when you have the 2 bigger groups are opposite to each other across that alkene unit. So the trans would be more stable than a geminal, more stable than a cis. What would be less stable than the di-substituted? Mono-substituted. What would be the least stable alkene unit? An ethylene, which is a CH2 double bond CH2. So that's how we basically rank the stability of alkenes. It's based on how many substituents sitting on that alkene unit. The more substituted the alkene is, the more stable it is. And that's what I want to talk about in this part. Next, we will be learning more about stability of cyclic alkenes, and we'll follow that by reactions of alkyl halides versus alcohols to generate alkenes.